In this video, we're going to look at integration by parts. Now, we've done integration by reversing the basic rules of derivatives. And then in a previous video, we've seen that integration via substitution is the reverse of the chain rule. Well, integration by parts reverses the product rule of derivatives. So using substitution to integrate reverses the chain rule of derivatives. Doing integration by parts is reversing the product rule of derivatives. So let's go back and review what the product rule was. So the product rule says if I want to take the derivative of the product of two functions, then what I can do is I can take the derivative of the first function multiplied times the normal second function plus the normal first function times the derivative of the second function. So derivative with respect to x of f times g is equal to f prime times g plus f times g prime. Now there's other notations you can use. You can use f of x, g of x if you'd like. Some people use u's and v's, but that's the basic idea of the product rule. So if we have something like x to the fourth times sine of x, and I want to take the derivative of that, I can take the derivative of x to the fourth, which is 4x to the third, multiply it times normal sine of x, and then add on the normal x to the fourth times the derivative of sine, which is cosine. So that is the product rule for derivatives. We have two functions multiplied together. So we want to reverse that. Basically, what I do is I take this product rule and I integrate on both sides. If I integrate on the left, then the integration of a derivative is going to give me back f times g, possibly plus a constant, but we'll leave that off for now. And then on the right-hand side, when I integrate the sum of two different terms, I can integrate the terms individually. So I integrate this term and then integrate this term. Now, after we integrate both sides, we have two integration pieces on the right. Basically, what we're going to do is we're going to solve for this integral here, the f prime times g integrated. And I do that by subtracting the integration of f times g prime on both sides. So that gives me that the integration of f prime times g is equal to f times g minus the integration of f times g prime. And that's what integration by parts is. So if we let f and g be differentiable functions of x on some sort of an interval I, then on that interval, the integration of f prime times g with respect to x is equal to f times g minus the integration of f times g prime. Now you might say, this is kind of weird because we start with an integration and our answer still has an integration in it. Well, what we hope for is that while this initial integration might be tougher to deal with, we hope that the second integration, the integration on the right, is easier to deal with. But that's the idea of integration by parts. And so what we're going to do is we're going to be given an integration. And when we want to integrate by parts, we have to determine which thing stands as the f prime, which thing stands as the g, and then I'll figure out from there the f, the g, the f, the g prime, and then hopefully this right-hand side can be easily dealt with. Now, there's lots of different options for integration by parts. In this class, we'll look at three basic types. One of the basic types is when we have a polynomial multiplied by a trig function or a polynomial multiplied by an exponential function. A second type is when we have a polynomial multiplied by a logarithm, specifically the natural log. And then the third type is going to be what happens when we have an exponential function multiplied by a trig function. So all three of these are going to be treated a little bit differently. I shouldn't say differently. We're always going to have an f prime and a g, but which one we call the f prime, which one we call the g is going to be important. So let's take a look at this example. We have 4x multiplied times e to the 5x. We want to integrate that with respect to x. So we're going to use integration by parts to integrate this one. Now, before I get the process here, I do want to mention that if you try to use one of the basic techniques, it's not going to work because we have function times function here. Also, substitution won't work because if I let u be equal to 5x, then I'll still have a u e to the u, which doesn't help me a lot. It'll change some numbers, but not going to help me a lot. So integration by parts is the right way to go. And in fact, it's the only way for this problem. That's the only good way. So the basics are that I need to call either the 4x the f prime, or I need to call the e to the 5x the f prime. And I need to call the other one the g. So this is the 4x e to the 5x is f prime times g. This 4x is a polynomial, and this e to the 5x is an exponential function. Now, for an example like this, it turns out I want my f prime to be the exponential function, and I want the g to be my polynomial. Now, the reason I want g to be the polynomial is because obviously I'm going to need an f, a g, an f, and a g prime over here on the right. So what I'm going to do is I'm going to figure out what f is, and I'm going to figure out what g is. The reason we like, oh, sorry, not f and g, f and g prime, excuse me. The reason why we like g being the polynomial is because if I take a derivative, you can see since this is a linear polynomial, the derivative of 4x is just the constant of 4. And constants are really nice to deal with. Now we'll see in a couple examples, if we take something like 4x squared, then it'll take a couple of derivatives until we get down to a constant. But the reason I'm using g prime, or excuse me, the reason I'm using g as the polynomial is because when I take the derivative g prime, it simplifies, the variable x goes away. Now, that's going from g to g prime. G to g prime is taking a derivative. On the other hand, going from f prime to f is integration. So I need to figure out the antiderivative of e to the 5x. Well, that's one of our basic rules. 1/5 e to the 5x is the antiderivative of e to the 5x. Or is at least one antiderivative. It doesn't matter which one you choose. It'll all turn out the same on the right-hand side. Constants will cancel out and combine and all that. So now we're ready to deal with our integration. So this was the integration of f prime times g. I know by my integration by parts formula that the integration of f prime times g is equal to f times g. That's 1/5 e to the 5x times 4x. So let me write that down. 1/5 e to the 5x times 4x minus the integration of f 1/5 e to the 5x. Oh, my bad. Times g prime. And we're going to integrate that with respect to x. So basically, what I get is that this integration becomes, let me rewrite this, 1/5 times 4x is just going to be 4/5 times x. E to the 5x minus the integration of, when I multiply that, that's 4/5 e to the 5x. So the integration that I'm looking for is this one. And you'll notice that the integration over here on the right-hand side is something that fits my basic rule. So all I have to do is do a simple integration on that right-hand side to see that my final answer will be 4/5 x times e to the 5x minus, well, when I integrate e to the 5x, I'll get e to the 5x. And then I'll have to divide by 5, so that 4/5 will become a 4/25. 4/5 divided by 5 is 4/25. And then at the very end, I'll tack on a plus c. By the way, that tack on of the plus c, that takes care of basically any constants up here that I could have added when I got my antiderivative. So I won't go through this, but if you do any antiderivative, if you do 1/5 e to the 5x plus 19, it would still come out to the same equivalent statement. So there we go. That is our final answer. The integration that I was looking for turns out to be this. So that's the final answer of this. And basically what happens is that when you take a derivative of this, if you were going to check your answer, you could take a derivative. The derivative, you would do derivative of 4/5 x, that would be 4/5, times the normal e to the 5x plus the derivative of e to the 5x times normal 4/5 x. So I take 4/5 x times the derivative of e to the 5x. The derivative of e to the 5x is e to the 5x times 5. If I take 4/5 times 5, I just get 4. And then if I take the derivative of negative 4 over 25 e to the 5x, derivative of e to the 5x is e to the 5x times 5. So I get minus 4/5 e to the 5x. And then what's happening, as you can see, this one and this one are opposites, so they cancel each other out, and you're just left with the original function that you were trying to integrate. So that's a good check that it works. And that's kind of why we get multiple terms, because if you just took a derivative of a single term, it's going to sort of double into two terms using the product rule. And so you need a second term, and that's going to cancel out, or a third term, I should say, and that's going to cancel out. So that's the idea of integration by parts. Now, in this case, I had a linear polynomial along with an exponential function, and I let my linear polynomial be my g, my exponential function be e to the 5x. Now let's take a look at example 2. Example 2 is going to be very similar. We have 2x times cosine of 8x. We want to integrate that with respect to x. Once again, I have a polynomial, but this time, instead of multiplying by an exponential function, I'm multiplying by a trig function. Well, the same technique is going to work. 2x cosine of 8x. I'm going to let the polynomial be the g part and the trig function be the f prime part. I'll show you how that's done. So, like I said, here we have polynomial times cosine of 8x. We're going to let the cosine of 8x be the f prime, and we're going to let the 2x be the g. And again, the reason why I'm doing that is because when I take the derivative of that polynomial, it turns out to be a constant. Now, be careful with f prime to f because you're taking the antiderivative or an antiderivative. So the antiderivative of cosine is positive sine. We have sine of 8x. Our argument is 8x. So in front, we're going to have to divide by 8. If you forget how to do that, that was one of the things we saw in our substitution section. So if our argument is 8x instead of just x, then we can, when you integrate, you divide by 8. But now we're ready to go. This cosine of 8x times 2x integrated is going to be f times g. The f is 1/8 sine 8x. The g is 2x. I'm going to multiply that together immediately, and I'm going to rewrite it as 1/8 times 2 is 1/4. So I'm going to rewrite it as 1/4 x times sine of 8x minus the integration of f times g prime without having to do another, let me actually just do another line, without having to do another step. I'll just do this in my head. F times G prime. Well, 2 times 1 over 8 is 1/4. So I get 1/4 times sine of 8x. And I'm going to be integrating that with respect to x. So now I have something in this integration that's easy to deal with. I can integrate sine, the antiderivative of sine is negative cosine. Notice I'm not doing any operations to this first one. There's no operations to do here. I just leave it alone. And so, again, antiderivative of sine is a negative cosine. So I'm going to do a negative of a negative cosine of 8x. And then I'm going to divide by 8. 1/4 divided by 8 is 1 over 32. And the negative of a negative is a positive, so I'm just going to call that plus. And then I can't forget at the very end to tack on a plus c to give me the set of all antiderivatives of 2x times cosine of 8x. So that's my final answer. When I take the antiderivative of 2x times cosine of 8x, I end up with these two terms. My first term is 1/4 x times sine of 8x. And my second term is 1 over 32 times cosine of 8x. And then obviously your plus c. If you did want to check this by hand, this 1/4 x sine of 8x, when you take a derivative, would turn into two terms. One of those would cancel out with the derivative of 1 over 32 cosine of 8x. But there you go. That is your final answer right there. So you can see how similar this is to when we had a linear polynomial times e to a power. Now we have linear polynomial times trig function. So here's another example that we can use where we have a linear polynomial multiplied times trig piece. So we have 10x times secant squared of x integrated with respect to x. If you want, push pause on the video and try this on your own, and I will just go ahead and solve this. I'll give just a couple of seconds if you do want to pause the video. All right, so let's do our f prime. Our f prime is going to be secant squared, and our g is going to be our polynomial. And again, we have a nice linear polynomial in this case as well, 10x. G prime is just 10. F, well, the antiderivative of secant squared, that's one of my basic rules, that's tangent. So obviously you could tack on any plus 2 if you wanted, but it's just tangent. So that means that the antiderivative or the integration of 10x times secant squared of x with respect to x becomes, well, f times g is going to be tangent times 10x. I'm going to write that as 10x times tangent. That is tangent of x. And then I'm going to subtract the integration of g prime, which is 10, multiplied times f, which is tangent. So 10 times tangent of x dx. So that's what we get. Now you may say, at this point, what is the antiderivative of tangent? How can we integrate tangent? We'll see this in the very next section, dealing with trig function substitution. All right. Um, I think for right now, I'm going to put that off and say in the next section, we'll see how to do it. So for right now, just trust me. And basically, I'm just going to say the antiderivative of tangent is actually negative natural log of cosine. Obviously, if we have negative times negative, that's a positive. So what I'm going to get is a positive 10 times the natural log of the cosine of x. So antiderivative of tangent is the negative of the natural log of cosine of x. We'll see how to do that, like I said, in the next section. So don't let that bother you right now. You can check it out here. If you do want to go look it up, you can just, Google that result too. How do you get antiderivative tangent, negative natural log of cosine? Oh, and always we have to add on plus t. So this is my final answer here. One thing I do want to mention that you'll often see with cosine is they'll do absolute values around the cosine because natural log can only take on absolute values. So or only positive values. So a lot of times they'll put absolute values around this cosine. I'm not doing that. So if that bothers you, just wanted to point that out, like usual. Now, in our first three examples that we did, we had a linear polynomial times an exponential, a linear polynomial times a trig, and another linear polynomial times a trig function. So all three of those examples, our polynomial has always been linear. What if we happen to have a quadratic or a higher degree polynomial as my coefficient? So let's take a look at this one, 12x squared times e to the 4x. We want to integrate that with respect to x. So we'll find the set of all antiderivatives. Okay, so when I go to do this, my f prime is still going to be my exponential function. My g is still going to be my polynomial. My g prime is going to be 24x, and my f, when I take the antiderivative of e to the 4x, one antiderivative is 1/4 e to the 4x. So now I'm set to use my integration by parts formula. So I start using that. f times g. Now 12 times 1/4 is going to be a 3. So I'm going to get 3x squared times e to the 4x. That's when I multiply f times g. Hopefully that makes sense. 12 times a fourth gives you the 3. I have an x squared. I have an e to the 4x. Minus, then I integrate f times g prime. So 1/4 e to the 4x times 24x. 1/4 times 24 gives me 6. So that's 6x e to the 4x. Then I'm integrating with respect to x. So I get that. Now in the previous examples, this piece in here gave me a basic antiderivative rule. However, now you'll see that piece inside the integration still is an integration by parts technique. In fact, this looks really similar to the first problem we did in example 1. So in other words, I have to do another integration by parts on this. Now, what I typically do is I typically take this negative sign and I distribute it on the inside. And I'll call my polynomial negative 6x. And then I have this exponential function e to the 4x. And I'm going to do another integration by parts just on this piece. So basically, what I've done is I've done one integration by parts with an f1 and a g1, essentially. And now I'm going to create a whole nother integration by parts using an f2 and a g2, a second integration by parts. So just like before, the f prime piece is going to be the exponential. Once again, that's going to be e to the 4x. The g prime, or excuse me, the g piece is going to be negative 6x. When I integrate to get my f2, my second f, we're going to get 1/4 e to the 4x. Sorry about that. And then when I take a derivative of g2, I just get a negative 6. So this entire thing becomes, well, I have to keep 3x squared e to the 4x there. So I keep that there, 3x squared e to the 4x. Keep that there. Plus f2 times g2. So f times g. In this case, if I take negative 6 times a fourth, I'm going to get negative 3 over 2. So negative 3 over 2, x times e to the 4x, minus an integration of f times g prime. Again, when I multiply those two, f times g prime negative 6 times a fourth gives me a negative 3 over 2 times e to the 4x. We want to integrate that with respect to x. You can see that by doing the distributing this negative sign in, by calling my G2 a negative 6x, at this stage, I don't have to distribute a lot of negatives. In the previous idea, I would have. So short of the story is, some people like to keep the negative on the outside. Some people like to distribute that negative in and call my polynomial a negative polynomial. Hopefully that makes sense. At this case, at this point in time, negative of negative, I know that's going to cancel each other out. And what I get is that 3x squared times e to the 4x minus 3 halves x times e to the 4x. And this is going to be a plus. Now, when we integrate this is just e to the 4x integrated times a constant. So we're going to get e to the 4x divided by 4. 3 halves divided by 4 is a 3 over 8. Negative times negative gives you a positive 3 over 8. So 3 over 8 e to the 4x is my last term in front of the plus c. And that is my final answer. So when I had a quadratic function, I essentially had to do an integration by parts formula once. That got me down to a linear piece. And then the linear piece, I did another integration by parts on that part. And then that broke down into a constant piece in front of the e to the 4x. And if you did want to check your answer, you could. Basically, this is going to split up into 2 parts. This is going to split up into 2 parts. And this is going to be 1 part. And essentially, we're going to have something like an A, a B. This is going to give you like the negative B, going to give you a C, and this is going to give you the opposite of C. I shouldn't say C, that's probably bad. And then derivative, this is a constant. I'm not saying that these C's are the same as this one. But that's what happens, basically. So 4 of these terms cancel out. And you're just left with that single term at the end. And that single term is going to be exactly what you want. It's going to be the 12x squared times e to the 4x. So in other words, you do a product rule here, you do a product rule here, you do a normal derivative here, and then you'll end up with 5 terms, 4 of which cancel out. And the remaining term happens to be the one I'm looking for. So that's how to do integration by parts with a quadratic. Now you can imagine if you did a cubic, if this were x to the third, you'd have to do integration by parts 3 times. And if this were x to the fourth, you do integration by parts 4 times, and so on and so forth and so on and so forth. And if you did something like, 12x to the fourth times e to the 4x, obviously you could do a lot of integration by parts, but you'd discover that there's some patterns to this, and you'd probably then try to go discover the patterns and how that works. Now, Let's just do one more integration by parts with a quadratic polynomial. This quadratic polynomial has multiple terms, and we're going to take that quadratic polynomial, x squared plus 3x plus 1, and multiply it times sine of x. And we want to integrate that with respect to x. Go ahead and push pause if you'd like and try this on your own. I'll give you a couple of seconds and then I'll do it as well. All right, so this is a quadratic. Therefore, I know I'm going to have sort of two integration by parts steps. If this were cubic, I know I need three. So let's do the first f and g. F prime is going to be sine of x. G is going to be my polynomial, x squared plus 3x plus 1. Derivative of g is 2x plus 3. F, well, the antiderivative of sine is negative cosine. Again, that's the antiderivative. When I go from g to g prime, I take the derivative. F prime to f, I take the antiderivative. So integration by parts formula says that this integration is going to be equal to f times g, x squared plus 3x plus 1 as a polynomial, multiplied times negative cosine. I think I'll put the negative out front. Minus the integration of f times g prime. So g prime is 2x plus 3. F is negative cosine. And I'll distribute that negative out front. Negative times a negative is going to give me a positive. So that's what I get when I do the first integration by parts. Now, here I have a linear polynomial times cosine. Trying to integrate that with respect to x is going to force me to do an integration by parts on this integration. So once again, I'll let my trig function piece be my f prime. I'll let my polynomial be my g. Derivative of g is just the number 2. The antiderivative of cosine is positive sine. So what's going to happen? What I'm saying is this integration, the original integration that I was trying to do, is going to be equal to this part. That part stays. Negative quadratic times cosine plus f times g, that is 2x plus 3 times sine of x minus the integration of f times g prime, which is just 2 times the sine of x. Integrating sine is pretty straightforward, hopefully. And therefore, my final answer is just going to be this thing, where I've integrated the 2 times sine. Again, antiderivative of sine is a negative cosine. So I get -2 times the cosine of x. And then I always have to tack on a plus c at the end. Now, negative of a negative gives me a +2, so I'm going to get this as my final answer. Notice that we're starting out with quadratic times negative cosine, and then I get the linear piece times regular sine, and then I get a 2 times a cosine. So notice negative cosine changes into a sine, changes into a cosine. Going down each time, pattern-wise, I'm taking the derivatives. And then x squared plus 3x plus 1, derivative of that is 2x plus 3. Derivative of 2x plus 3 is 2. So you can kind of recognize that there is going to be a pattern of derivatives as I go down. And if you check the previous question, it's the same way, although it's slightly more complex there. So there we go. That's the idea of how to do integration by parts. Like I said, I started out with a quadratic here, and that took me 2 integration by parts formulas to do. I had to apply essentially 2 integration by parts steps. If I start out with a cubic, I'd have to apply 3. A quartic, I'd have to go 4. Quintic, I'd have to go 5. And then at that stage, you just start recognizing some patterns of how these things operate. Hopefully that makes sense. Now, what we just did was this first type of integration by parts, the polynomial multiplied by a trig function or polynomial multiplied by an exponential function. And that trig function, by the way, just had x in the argument. The exponential function had just x in the argument, or maybe 5x or 8x, or constant times x in those arguments. So whenever we did that, the polynomial became our g in our integration by parts formula. Now we're going to look at what happens when we have a polynomial multiplied by a logarithm, or in particular, times a natural log. In this class, we use natural log a lot. If you were utilizing a different base on your logarithm, you could just change a base formula into a natural log if you'd like. So let's take a look. Let's take this same polynomial we just dealt with, and instead of multiplying it by sine of x, let's multiply it times natural log of x. And let's use integration by parts to integrate this one. Now, because in my notes I have it separated as very much different than the exponential function, how we're going to deal with the exponential function and how we're going to deal with the trig function stuff when I have polynomial times exponential, polynomial times trig. Basically, that gives you a hint that we're going to deal with this differently. Now, I want to explain why we're going to deal with this differently. If I were to have put my polynomial as my g of g, then the g prime would be fine to deal with, okay? But that would have forced me to put natural log of x as my f prime. Now, the trouble with that is right now, we do not know what the antiderivative of the natural log of x is. We know a derivative for natural log of x. The derivative of natural log of x is 1 over x. But the antiderivative of natural log of x, we haven't covered yet. So that forces me to do the reverse thing. That forces me to have my g as natural log of x, so that when I take a derivative, I can get 1 over x. And that means the polynomial is going to be my f prime. So if we have natural log or any other base, but we're just going to use natural log in this class, then we let the g be equal to natural log and the f prime be the polynomial. Now, the polynomial, when I take an antiderivative, becomes 1/3 x to the third plus 3/2 x squared plus x, or plus 1x. But that's fine. That's perfectly fine. Let's see how this is going to work out. So we're trying to integrate this. This is what we call my f prime times g integrated. So I need to take f times g. F is this ugly polynomial times g, which is natural log of x. Let me write that down. The ugly polynomial is 1/3 x to the third plus 3/2 x squared plus x. Make sure you put that in parentheses when you multiply it times natural log of x, because the entire polynomial is being multiplied times natural log. Minus f times g prime integrated with respect to x. Now, once again, f is this ugly polynomial. But g prime is 1 over x. And something really nice happens here. What's going to happen when I multiply any polynomial times 1 over x? Well, it simplifies. In short, it simplifies. When I take 1 over x times x to the third, one of the copies of x is going to cancel with the x in the denominator. And what I'm going to get is, let me put this in parentheses. So what's going to happen is that x to the third times 1 over x is going to become x squared. And the x squared times 1 over x becomes x. And the x times 1 over x becomes 1. And now I'm just integrating a polynomial. So the fact that the derivative of natural log of x is 1 over x means it works really nicely in conjunction with polynomials, because I can multiply 1 over x times any polynomial, and then the degrees of each term just go down by 1. So this is what we get. We get our 1/3 x to the third plus 3/2 x squared plus x times natural log of x. Oh, minus, well, when I integrate, I'm going to integrate and put the entire polynomial into parentheses. We're going to get 1/9 x to the third plus 3/4 x squared plus 1x, and then plus c at the very end. I got to tack on that plus c. So I get my polynomial times natural log of x minus, again, in parentheses, this polynomial plus c. If you want to distribute the negative sign into all three terms here, you can, but that's the basics of it. Again, you can also distribute the natural log times all three of these terms as well. I'm not going to do that. I'm just going to write it this way. So if I want to find the antiderivative of x squared plus 3x plus 1, all multiplied times natural log of x, I get this. 1/3 x to the third plus 3/2 x squared plus x, all times natural log, minus the entire polynomial, 1/9 x to the third, 3/4 x squared plus x, plus, and then add a tack on that plus c at the end. So again, if we have polynomial times natural log, let the natural log be g, so that when I take a g prime, that interacts very well with any polynomial, through multiplication anyways. Hopefully that makes sense. Now you'll notice that we started with a quadratic, but it only took us one integration by parts to do it. In fact, with natural log, since we're dealing, the g becomes natural log. Since we're dealing with it this way, it doesn't matter the degree of this polynomial. We could have a very large degree polynomial times natural log, and it would just take one integration by parts formula to figure that out. So let's do an example just like that. Let's take a large degree polynomial. Let's take x to the 17th times natural log, and let's integrate that with respect to x. So basically, we're going to use the same process as we did in the last example. We have polynomial times natural log. We want to use integration by parts. In fact, this is really the only way this can be done, is by using integration by parts. So we let g be the natural log of x, and then g prime becomes 1/x. In this case, our polynomial out front is x to the 17th power. If I want to take an antiderivative of that, it'll be 1/18 times x to the 18th power. So that means my integration is going to be equal to f times g, that's 1/18 times x to the 18th power, multiplied times natural log of x, minus integration f times g prime. I'll do the steps here. The f is 1/18, x to the 18th power, g prime is 1/x. So then I just have to algebraically manipulate this and then integrate it. So I have 1/18 x to the 18th power multiplied times natural log of x minus integrate 1 over 18 times x to the 18th times 1 over x. All that's going to happen is that 1 over x times x to the 18th becomes an x to the 17th. So I get 1 over 18 x to the 17th power integrated with respect to x. That is fairly straightforward to integrate. So the first term is 1 over 18 x to the 18th power times the natural log of x. That always just stays the same. And then I have minus, well, when I integrate x to the 17th, I'm going to get an x to the 18th, and I'm going to divide 1 over 18 by 18. So that becomes 1 over 324. 18 over 18, to me, 18 times 18 is 324. So I get 1 over 324 times x to the 18th, and then I have to tack on my plus c at the end. So there we go. That's what happens. That's how we deal with that. By the way, this may be a good time to point out that if, I know I've said this explicitly, but if you would have used a different antiderivative to go from f prime to f, let's say we would have tacked on the constant, I don't know, let's do the constant of 7, all right? I tack on a plus 7 at the end. Then what would happen is this would change into 1 over 18 x to the 18th plus 7. There'd be a plus 7 in here. And then when I take 7 times 1 over x, I would get 7 over x. And then when I integrated, my answer would have had 1 over 18 x to the 18th plus 7 times natural log of x minus 1 over 324 x to the 18th. And then what happens when I integrate 7 over x is I get 7 times natural log. And what's happening here is this 7 times natural log, this is a plus 7 times natural log. When I distribute this negative symbol, I would end up with a minus 7 times natural log. So this 7 natural log here and this 7 times natural log here, when I distributed, would both cancel out, and I'd get exactly the same thing as if I'd had 0 as my constant. So that's why, for the most part, we just use a plus 0. That'll happen in every single instance of integration by parts, as if you tack on a plus a constant in this step, in that last step, you'll get canceling outs and the constants will go away. So that's why we typically don't tack on any constants. But It's good to point that out at least once, that if you did take a different antiderivative, you'd get the same answer. So we've seen now a couple of examples of where a polynomial is multiplied by a logarithm. And we saw one where we had multiple terms times this natural log of x. We had one of a really high degree times natural log of x. Using integration by parts only forces us to do one integration of parts step in order to actually integrate a polynomial times natural log. So you can have a really, really ugly polynomial of high degree of lots of terms times natural log, and it still only takes one integration by parts step to integrate. Now, I had mentioned that one of the reasons that we want to let that polynomial be our f prime is because we don't have an antiderivative for natural log of x. Well, it turns out that integration by parts can actually be used to find the antiderivative of natural log of x. So let's say we want to integrate natural log of x with respect to x. So how does integration by parts help? Well, it helps because natural log of x by itself is just like a polynomial of 1 times natural log of x. And if I think of the coefficient of 1 as being the polynomial I'm using, and then the natural log of x being obviously natural log of x, the 1 can be my f prime. The natural log of x can be my g, just like usual. G prime is 1 over x. If I take the antiderivative of 1, I just get 1x. So this means that if you want to take and integrate natural log using integration by parts, we should get f times g, which is x times natural log of x, minus the integration of f times g prime. That's 1 times 1 over x, integrated with respect to x. Now, x times 1 over x is just 1. So we get x times the natural log of x minus the integration of 1 with respect to x. If I integrate the constant of 1, I just get 1x. So my final answer is that when you integrate natural log with respect to x, you actually get x times natural log of x minus 1x. And then obviously I have to tack on a plus c at the end. So if you look up the antiderivative for natural log of x, or if you look up how to do an indefinite integral of natural log of x, it'll give you this formula that it says, well, the antiderivative of natural log of x is x times natural log of x minus x plus some constant. And so that is actually how we come up with figuring this out. Now, knowing this fact actually doesn't help you in our previous couple of problems. If we would have tried to switch around the f prime and the g, would not have worked nearly as well. So every time we deal with polynomial times natural log, the polynomial becomes our f prime, natural log becomes your g, and then we apply the integration by parts formula. So every time we're in that scenario, we do that. So now we know not only how to do integration by parts with a polynomial times natural log, now we know the integration of natural log, which we didn't earlier. So with polynomial times a trig function, we let the trig function be the f prime. With polynomial times exponential, we let the exponential be the f prime. With polynomial times logarithm, we let the polynomial be the f prime. What if we have a combination of trig function and exponential? We won't do a combination of trig function logarithm here, exponential and logarithm. But what if we have an exponential times a trig? Something like this. Now, this is another technique of integration by parts. This is another setup where integration by parts works nicely. But it's kind of what I'll call a clever integration by parts. We have to think through how we want to do it. So we want to integrate sine of 4x times e to the 2x with respect to x. So this is trig function exponential. If we start taking derivatives, exponential is just going to keep there. If I just take a derivative of e to the 2x, I get e to the 2x times 2. I take another derivative, I get e to the 2x times 2 times 2, so 4 e to the 2x, and it just never goes away when I start taking derivatives. When I start taking derivatives of sine of 4x, I'll get cosine of 4x times 4, then negative sine of 4x times another 4, so that'd be times 16, and then another derivative will give me negative cosine of 4x times another 4. So when I start taking derivatives of trig functions, they don't go away either. So I'm going to have to treat this differently than I did with a polynomial times a trig function or a polynomial times an exponential, because the derivatives here essentially never go away. They change, but they never go away. Never become a constant number, in other words. Now, I'll just prep you. It turns out we're going to have to do two integration by parts formulas in order to solve this problem. So I'll do this with subscripts. And it also kind of turns out that it doesn't matter which one you call your f prime and which one you call your g. So I think I'll call my f prime e to the 2x. And I'll call my g sine of 4x. So if I integrate e to the 2x, I get 1/2 e to the 2x. If I take a derivative of sine of 4x, I end up getting 4 times the cosine of 4x. The reason I chose sine as my g was simply because if I took a derivative there, it becomes positive cosine. I'd rather deal with positives than negatives. If I would have integrated, I would have had to be dealing with a negative cosine. But it doesn't matter. You could have said e to the 2x is your g and sine of 4x is your f prime, and went on your merry way that way as well. So here we go. F times g is going to be, in this case, 1/2 e to the 2x multiplied times sine of 4x minus, I want to integrate f times g prime. When I take f times g prime, 4 times 1/2 becomes a 2. Then I'll get e to the 2x cosine of 4x. Okay. Now, this integration does not simplify very well. I can't, that's not a basic rule. That's still trig function times exponential or exponential times trig. So what I'm going to do is I'm going to distribute that minus sign, and I'm going to do another integration by parts on this integral. So we're going to go f sub 2. We're going to have a second f and a second g. Excuse me. So a second f prime and a second g. All right. So once again, it doesn't really matter, but just to stay consistent, since I use the exponential function as my f1, I'll use this new exponential function as my f2 prime. So f2 prime is going to be negative 2 e to the 2x. Actually, you know what I'm going to do? I'm going to call that a positive 2. And then I'm going to be a little bit clever. I'm going to call the g2, I'll put the negative cosine of 4x as my g2. Now, if I take the antiderivative of the f prime, I'll get f. E to the 2x, the antiderivative will be e to the 2x, and then I divide by 2. So coefficient here was originally 2. Now I'm dividing by another 2. I get a new coefficient of just 1. If I take the derivative of cosine, I get negative sine. So negative times a negative becomes a positive sine of 4x. And then I have to multiply times the derivative of the inside function, which is 4. So what I'm saying is that this integration, I now know, is this 1/2 e to the 2x sine of 4x plus, I had a plus here, f times g, my new f, new g, that's going to give me a negative e to the 2x times cosine of 4x minus the integration f times g prime. I'll put the 4 out front. That's going to be 4 e to the 2x times sine of 4x. Now you may think that didn't help me. I still have now an exponential function and a trig function in here. And if we were trying to do a solving finding this integral directly, we'd be kind of out of luck because we'd have to do another step here and another step here, another step here. But I want you to notice that e to the 2x sine of 4x is inside this integral here. We've just multiplied by a constant of 4 out front. That's the same integral that we started with. So in essence, what we have, I'm going to rewrite this, is one big equation excuse me, one big equation. And if I pull that 4 out front, then I have this integration is equal to this thing minus 4 times the same integration. So what I'm going to do is I'm going to add 4 times that integration to both sides. So I add 4 times the integration of e to the 2x sine 4x dx to both sides. When I add 4 to the right-hand side, this whole 4 times the integral to the right-hand side, this piece goes away. When I add 4 times the integral to the left-hand side, I get 5 copies of the integral on the left-hand side. So what I just got is that 5 copies of this integral is equal to this mess. So all I have to do is divide by 5, or in other words, multiply by the reciprocal of 5 to figure out my answer. So I multiply by the reciprocal of 5 on the left-hand side. On the right-hand side, multiply by 1/5. And then there is one other little thing I have to do. I have to tack on a plus c, because when I actually added this integral to both sides, these are going to be the same except for possibly a constant difference. So I have to add on a plus c at the very, very end. But that is my final answer. Now, if you wanted to, you could have easily multiplied that 1/5 in. 1/5 times 1/2 is 1/10. If I multiplied the 1/5 over there, I'd get 1/5 e to the 2x times cosine of 4x. So if you wanted to multiply the 1/5 times both terms here, you could. But this tells you that the antiderivative, or the integral that I was looking for, turns out to be 1/10 e to the 2x times sine of 4x minus 1/5 e to the 2x cosine of 4x plus c. So basically what we did is we did an integration by parts once. That gave us cosine in there. A second integration by parts, and we got back our original integral times a constant. And if our integral is equal to a big mess minus our constant times the same integral, then I can just add this piece to both sides and combine like terms, and that gets rid of the integral on my right-hand side. A simple multiplication by the reciprocal gives me my final answer. So my final answer here is that this integration, this is the one I was originally looking for, is equal to this. That is my final answer. So it's kind of a clever trick. And that's how we deal with this exponential times a trig function. We let one be f prime and the other be g, and it didn't matter which one. It turns out if you would have flipped the f prime and the g, the roles initially, then it would have worked out in the exact same way. Okay, a little bit different path to get there, but would have worked out in the exact same way. So integrate twice using integration by parts, and then move that integration over. So here's another one where we have a trig function times an exponential. You can try this on your own if you'd like. If you'd like to, just pause this video if you want to try this on your own. I'm going to give a couple seconds and then I'm going to do the problem. Now that we've seen one example, we can do the others. We know that we're going to have trig function times exponential. We're going to have to do two integration by parts and then do that algebraic technique of moving the integral over. So cosine of x times e to the 5x, it doesn't matter which one I put where. I think this time, well, last time I put e to the 5x, I put the exponential as f prime. So this time I'll do it in reverse. I'll put the exponential piece as my g, and I'll put the trig piece as my f prime. Now, it doesn't matter that you do that. You could have done the opposite just as easily. Maybe I will do the opposite in a quick way in a second. So the antiderivative of cosine is a positive sign. The derivative of e to the 5x is 5 times e to the 5x. So when we set this up, this integration becomes f times g, that's e to the 5x multiplied times sine, that is sine of x, minus the integration of f times g prime, so that's 5e to the 5x multiplied times sine of x. And we're integrating that with respect to x. Now the first piece is just fine, but the second piece, I'm going to distribute a negative sign. And then I need to do a second integration by parts on this component, this negative 5 e to the 5x sine x. I think once again, I'm going to use, since I used e to the 5x as my g, I'm going to use 5 e to the 5x as my g on the second one. And I'll use negative sine of x as my f prime. If I do an antiderivative of negative sine, that's actually a positive cosine. And a derivative of 5 e to the 5x is 25 e to the 5x. So that means, excuse me, this original integration that I was trying to find is equal to e to the 5x sine x plus, okay, now we do f times g. F is cosine, g is this 5e to the 5x. So 5e to the 5x times cosine of x minus the integration of f times g prime. That's 25 e to the 5x times cosine of x. And sure enough, once again, other than that constant of 25, I got the same integration as I started with, e to the 5x times cosine. E to the 5x times cosine. So we're going to take this and we're going to create an equation with that expression. I think I'm going to go on to the next page. Yep. I'll make that a little smaller. So it fits on one line. And then we're going to add that, well, I'm going to add 25 because I can factor out this 25. I can pull it out front. So I'm going to add 25 times the integration of e to the 5x times cosine of x to both sides. So I add 25 times that integration to both sides, times that integral to both sides. If I do that, what happens, well, let me just rewrite this. If I add 25 times the integral to the left-hand side, I get 26 times the integral, 26 copies of the integral. And then on the right-hand side, this right-hand integration goes away. And now I would multiply by 1 over 26 on both sides. If I multiply times 1 over 26, what I'll get is, excuse me, 1 over 26 times this first term, and then 1 over 26 times the second term gives me a 5 over 26 as the coefficient of the second term. And then lastly, I always have to, every time I integrate, tack on that plus c at the end. So that's the class of antiderivatives there. So that's my final answer. My final answer is that the antiderivative of cosine times e to the 5x is 1 over 26 e to the 5x times sine plus 5 over 26 e to the 5x times cosine plus c. Now, I did this whole process where I put the e to the 5x as the g, and my initial choice of f prime was cosine. It turns out if you'd have flip-flopped that, you should get the same answer. Let's see if we get the same answer if we flip-flop. So I'll try to do this really quickly. Obviously, if you're not interested in this, you can just skip to the next example. But let's see what happens. So if I take a derivative of cosine, I get negative sine. I'll go through this pretty quickly. If I take an antiderivative of e to the 5x, I get 1 over 5 times e to the 5x. My new f prime would, my new f times g, that'd be 1/5 e to the 5x 1/5 e to the 5x times cosine minus f times g prime. Now I have a negative sign in there, so when I take a negative sign and I have this minus out front, that's going to switch it up to a positive. I'm going to get 1/5 e to the 5x times sine. So it's going to be a positive 1/5 e to the 5x times sine. And then, well, since I dealt with this before, let's do it the same way I did up here. The exponential is my f prime. So exponential 1 over 5 e to the 5x. That's my f prime. And then my trig function will be my g. We'll get 1 over 25 e to the 5x as my f. And the g prime will be cosine. So we're going to take this thing and we're going to replace this integration with f times g. Minus the integration of f times g prime and there we go. So once again, we have these e to the 5x times cosine of x integrated, although I have a new coefficient of 1 over 25. That's not going to hurt anything because I'm going to set it up in the exact same way. Let's make that a little smaller. There we go. And I'd factor out a 1 over 25. And so I'd add not 25 times the integration, but I'd add 1 over 25 times that integration to both sides. Now, be careful about this. When you add 1 over 25 to both sides, what you're getting on the left-hand side is this coefficient is a 1, really. So 1 plus 1 over 25 is a 26 over 25. So what we're getting on the left-hand side is 26 over 25 times the integration that I want. On the right-hand side, that integration goes away. This piece goes away. And then what I would do is I would multiply by the reciprocal of 25 over 26. Excuse me, I misspoke. I'd multiply by the reciprocal of 26 over 25, which is 25 over 26. So I'd multiply both sides by 25 over 26. And if I multiplied this first equation by 25 over 26, you'll notice that 25 times 1 will give you 25. This 5 and A5 will cancel, so you get 5 over 26 as your coefficient of e to the 5x cosine of x. And then when I multiply 25 over 26 there, I'm going to get 1 over 26 times e to the 5x sine x, and then tack on a plus c, which is exactly what we got here. We got 5 over 26, e to the 5x cosine of x, and then 1 over 26, e to the 5x sine x plus c. So whichever path you choose, it will end up with the same answer in the end. But it might have different numbers along the way, different coefficients along the way that I have to deal with. In any case, the main goal is to see when we have a trig function and an exponential function, we can do integration by parts once, then do integration by parts on this interval. So a second integration by parts, and then the integration that I was trying to find will show up again in this integral. And so we can algebraically manipulate that to find our answer. Don't forget to tack on the plus c at the end because that's important. And especially in this one, when you're moving this integration, a lot of times people forget that there's a constant that goes along with this integration that has to, pop out there. So now we've covered the three types of integration by parts questions that I would ask. The ones that you'd have a polynomial times trig or polynomial times exponential function, the ones that you have polynomial times logarithm, and then now lastly that exponential multiplied by a trig. And in that exponential multiplied by a trig, we do two integration by parts, and then we get back a constant times our original integration we were trying to find. Now, the last thing that I'll point out in this chapter, or this section, excuse me, not this chapter, but this section, is that we can find definite integrals using integration by parts. So for instance, if I wanted to integrate this from 0 to pi, instead of just finding the antiderivative, well, this is something we just found. So what I could do is I could simply plug in 0 and plug in pi into the antiderivative we just found and figure that out. So like I said, we just figured out how to integrate that. So if I'm going to go and integrate a definite integral from 0 to pi, I can just take this, I'll use constant of 0. And then plug in, let me use a different font size just so that we can have this look a little bit nicer. There we go. So I'll plug in pi. Everywhere I see an x. And then I'll plug in 0 everywhere I see an x. And then I subtract the 2, right? So once we've done integrals, we can find definite integrals using that. Now, the nice thing about this is that sine of 0 is 0, and sine of pi is also going to be 0. So what happens is this term turns into a 0, and this term turns into a 0. And cosine of pi is a -1. Cosine of 0 is a +1. Also, e to the 0 is a +1. So basically, I get, this is my final answer. I get -5/26 minus 5/26 times e to the 5 pi. So that's the actual numerical answer. And you can get an approximation of that by plugging that into your calculator. And it's something really, really big. About -127,6081. I'll say 0.73, but basically -1,278,081.73. Now, I typically don't do that. I typically skip right to this last step, and I typically don't do definite integrals here because usually we have technology. And sure enough, if you want to do an integration using technology, you can go integrate cosine of x times e to the 5x with respect to x from 0 to pi, and you should get the exact same answer. All right. Now, if somebody wants the exact answer, then you kind of have to do it by hand. But if somebody just wants an approximate answer rounded to 2 decimal places, then it's a lot easier to just use technology to come up with this than to plug things in and solve. So in short, you can use these techniques of integration by parts to solve definite integrals. Although if you're comfortable with an approximate answer, it's a lot easier to use technology to compute those. Now, again, integration by parts is one technique of many. We saw substitution. We've seen some basic rules. You can actually use integration by parts in things like sine times cosine integrated with respect to x. But integration by parts is not a very useful and effective way to do that. It's not the most effective. You can use integration by parts with exponential times exponential, but it's going to be a lot easier to just say, well, actually, exponential times exponential, utilizing some algebraic techniques, that's going to be e to the 8x when I combine those. So that's just integrating 14e to the 8x. We'll see how to do integration of sine times cosine in the next section. But my point is, integration by parts is one of many techniques. We saw basic substitution, we saw basic integration, we saw substitution to do integration, and now we've seen integration by parts. Okay? We'll keep on looking at more and more and more techniques as we move forward in these sections. But again, integration by parts is one of a lot of tools.